California sits astride a great tectonic seam where the Pacific plate slowly slides past the North American plate, and that slow motion, measured by satellites and on the ground, is on the order of 30 to 37 millimeters per year, which is about 1 to 1.5 inches per year. That steady, almost imperceptible drift is the engine that loads elastic strain into the crust over decades and centuries. Those tiny increments add up until the friction that holds blocks together on a fault is overcome and the crust slips in an earthquake. But the story of California's seismic hazard is not a single line on a map. It is a braided network of faults, each with its own character, slip rate, history of past ruptures, and stretches that have gone quiet long enough to be called seismic gaps. To understand the real risk, you have to look region by region, fault by fault, and pay special attention to places where strands meet, split, or are bridged at depth. And nowhere is that more consequential than in and around the junction of the San Andreas and Calaveras faults. Across the state there are on the order of 15,000 mapped faults, and more than 500 of those are considered active on human time scales. The most famous is the San Andreas, a right lateral strike slip fault that snakes for roughly 1,300 kilometers, about 800 miles, from the southern end of the state up toward the north. Even so, the San Andreas is only part of the picture. Parallel and branching systems carry a significant fraction of the plate motion. The Hayward and Rodgers Creek faults run through the Bay Area. The Calaveras fault dives under the southern part of the bay. The San Jacinto and Elsinore zones take much of the motion inland of Los Angeles, and farther east, the Walker Lane and Eastern California Shear zone accommodate a substantial portion of the deformation across the basin and range. Each of these systems is a potential source of damaging shaking, and many contain stretches that have not ruptured in recorded history. Those are the seismic gaps that worry geologists and planners. In the San Francisco Bay region, the Hayward Fault is perhaps the most politically charged because it threads densely built areas and last produced a large rupture in the year 1868, when it generated an earthquake of roughly magnitude 6.8. Since that time, the fault has been active in small ways. Some parts creep slowly, moving a few millimeters per year, while other parts remain locked and accumulating strain. The absence of a large rupture on the northern portion of the Hayward in historical times is notable. Paleoseismic evidence shows large earthquakes do occur there over longer intervals, but the gap since the last big event is long enough that many scientists consider the Hayward a high-hazard segment. The Rodgers Creek Fault across the Richmond and Santa Rosa area connects with the Hayward system in a way that makes the pair effectively a through-going hazard, depending on geometry and stress conditions. Ruptures could propagate from one to the other, turning two moderate segments into a single, longer and more powerful rupture. The Calaveras Fault is an underappreciated and structurally important player in the Bay Area. It branches and splays beneath the southern bay, running near and beneath suburban and urban centres to the south of San Jose. Parts of the Calaveras creep at the surface near Hollister, but other portions are locked at depth and have a history of moderate earthquakes, such as the event near Morgan Hill in the year 1984 that was roughly magnitude 6.2. Because the Calaveras lies so close to the southern end of the Hayward and to the San Andreas in places, its state of stress and potential for rupture are intimately tied to adjacent fault behaviour. Paleoseismology and geodetic surveys suggest that parts of the Calaveras have accumulated substantial strain since their last larger quakes, creating seismic gaps that could be sites for future ruptures. The San Andreas itself is not uniform along its length. Through the coastal and central regions there are patches that creep, patches that are locked, and long stretches that have not broken in large events for more than a century. The northern portion of the San Andreas famously produced the great earthquake of the year 1906, a rupture on the order of magnitude 7.8 that broke several hundred kilometers and devastated cities in the Bay Area. Farther south, the great earthquake of the year 1857, sometimes called the Fort Tejon event, ruptured a very long central and southern section with a magnitude approaching 8. Between those great events lie segments that behave differently. In some areas, the fault slips aseismically and releases energy slowly, while in other areas, elastic strain builds until it must be released in abrupt failure. This patchwork is the origin of seismic gaps, long intervals since the last large rupture on a given locked patch. In the Central Coast and parts of Southern California, locked stretches of the San Andreas remain overdue by historical standards if you average recurrence times inferred from Paleoseismic records. Where the San Andreas threads past the Bay Area and bends through the coast ranges, it interacts with a web of subsidiary faults. The Hayward-Rodgers Creek system, the Calaveras fault, the Concord and Green Valley faults, and multiple blind or shallow strands together form a complex three-dimensional architecture. At the surface map, these appear as distinct lines, but geophysical imaging shows that at depth the planes can dip, step over, intertwine, and even be linked by cross-cutting faults. One critical locality is the junction near the Hollister and Pinnacles region, where the San Andreas and Calaveras come into close proximity, and where the rock types and subsurface geometry create conditions that both facilitate and complicate rupture linkage. There, serpentinite and other slippery rocks can act as lubricants on fault surfaces, promoting creep in some places while creating brittle, locked contacts in others. Recent geophysical studies reveal that smaller cross-faults can bridge the San Andreas and Calaveras at depth, so a rupture that starts on one strand can, under the right circumstances, step across into the other. That potential for cross-fault propagation is exactly what makes the Junction region a seismic focal point. It is not just the sum of two lines, but a three-dimensional node where stress and slip can reorganize suddenly. Moving south into central California, the faults that splay off and around the San Andreas continue to matter. The Carrizo Plain and Cholame section of the San Andreas includes patches that are relatively locked and long enough to produce very large quakes. The Parkfield area, by contrast, is a stretch that has exhibited frequent moderate shocks every few decades in the past, an observation that inspired many focused studies of the fault's behavior. To the east, the Garlock fault cuts across the Mojave in a left lateral sense, acting as a structural boundary and occasionally interacting with transfers of stress from large events on the San Andreas or other southern faults. Even when a fault such as the Garlock moves only a few millimeters per year, its geometry and intersections with other faults can localize stress and influence where ruptures start, stop, or transfer. In Southern California, the picture becomes even more crowded. The San Jacinto fault zone runs roughly parallel to the San Andreas, and in many places appears to take a significant fraction of the plate motion. Several strands within the San Jacinto system exhibit relatively high slip rates, on the order of 12 to 14 millimeters per year, which is about 1/2 an inch per year, and some of its longer segments have not hosted major ruptures for centuries. Geologists have identified what they call an Anza seismic gap on the southern part of the San Jacinto, a stretch perhaps on the order of 90 kilometers long, which has gone unbroken since before recorded colonial times. Paleoseismic data indicate a long recurrence interval there and a build-up of strain that would support a substantial earthquake when it finally gives. West of the San Jacinto lies the Elsinore fault zone and other lesser slipping strands such as the Newport-Inglewood Fault in the coastal Los Angeles Basin. These are shorter but closer to dense populations and therefore significant for hazard because short faults that rupture close to urban centres can be exceptionally damaging even if they're not capable of the very largest magnitudes. The Los Angeles region also contains numerous blind thrust faults and buried structures that do not break the surface. The devastating earthquake at Northridge in the year 1994 occurred on such a hidden reverse fault in the Los Angeles Basin and showed how damaging shaking can arise from faults that were not included on earlier surface fault maps. Those basin faults and the subsurface sedimentary basins themselves amplify seismic waves. Deep alluvial basins can trap longer period energy and thus affect tall structures, while shallow, soft sediments amplify higher frequency shaking that impacts smaller, stiffer buildings. Thus, hazard depends not only on which fault ruptures, but on how seismic waves propagate through three-dimensional crustal structure and how they interact with local soils and basins near population centers. Beyond the principal plate boundary systems, the Eastern California Shear Zone and Walker Lane region absorb a non-trivial portion of the relative motion. These distributed strike slip and normal faults extend northward through Owens Valley and into the interior and have produced large magnitude events in the past, such as the Great Owens Valley Quake in the year 1872. Even though individual strands in this broader zone may slip only a few millimeters per year, their collective contribution and their intersections with the main right lateral belt make them important in the probabilistic tally of where and when significant earthquakes will occur. A central theme across all these systems is segmentation. Faults are not uniform, they contain bends, step-overs, changes in dip, and intersections with other faults. Those structural irregularities concentrate stress and can act either as barriers to rupture propagation or as places that facilitate rupture jumping, depending on rock properties, stress orientation, and the dynamic stresses produced as a rupture advances. The dynamic process of rupture begins at a small nucleation site, a hypocenter, and then the failure front spreads across the fault surface. In some conditions, the rupture can accelerate to very high speeds and may even achieve supershear speeds, analogous to a sonic boom for seismic waves, which concentrates energy and enhances shaking intensity along certain directions. Whether a rupture will stop at a geometric irregularity or leap across to a neighbouring strand is a question of local stress, frictional properties of the fault contact, and the exact sequence of slip as the event unfolds. Laboratory friction experiments and field observations show that patches of a fault can be frictionally unstable. When slip begins to accelerate, friction can drop, allowing a small patch to cascade into a larger dynamic rupture. Because faults interact, one earthquake can change the stress state on nearby faults. When one segment slips, it relieves shear stress locally, but can increase shear stress on adjacent sections or alter the normal stress that clamps fault surfaces together. These Coulomb stress changes are directional and spatially complex. A rupture may make a nearby patch more likely to fail, and another patch less likely for a period of time. That is why a big event on one fault sometimes appears to trigger sequences of earthquakes on neighbouring faults, and why clusters of earthquakes in space and time are common in tectonically crowded regions. The junction of the San Andreas and Calaveras is a textbook example of such potential interaction. Its three-dimensional complexity, cross-fault linkages, and variable rock types make it a place where a moderate rupture might cascade into a larger multi-fault event under the right circumstances. Paleoseismology, the study of prehistoric earthquakes preserved in layered sediments and offset landforms, provides a long view of which segments have ruptured and at what intervals. Where trenches reveal repeated surface ruptures, it is possible to estimate recurrence intervals and to identify stretches that have gone long enough without a major event to be called seismic gaps. However, recurrence times vary widely and are not strictly periodic. Some segments show characteristic behaviour with relatively regular, moderate quakes. Others show long, quiescent intervals punctuated by very large, rare events. The variability and the incomplete record mean that a seismic gap is a signal of elevated concern, but not a precise clock. Modern geodesy, using continuous global positioning network stations and satellite interferometry, adds the present rate of strain accumulation to the historical record. When ground deformation shows that a particular patch is accumulating elastic strain at a higher rate than surrounding areas, that patch becomes a candidate for future rupture if it is locked. Conversely, observed surface creep may relieve some portion of strain at shallow depths, but does not necessarily free the deeper locked portion. Therefore, coupling between shallow and deep behaviour matters. A fault that creeps at the surface can still harbour a locked deeper patch that is accumulating enough strain for a large earthquake. What does all this mean for the headline numbers you sometimes see? Like a stated probability that a region has a 72% chance of experiencing a particular size earthquake over a specific time window, those numbers are shorthand summaries of a much larger probabilistic calculation. Scientists compile inventories of fault segments, estimate their slip rates and plausible magnitudes based on length, and use paleoseismic and instrumental catalogues to inform the likelihood of different rupture sizes. Importantly, modern community forecasts explicitly allow for multi-fault ruptures. Instead of insisting that events are confined to a single named fault, they consider scenarios where adjacent segments can link, producing a longer rupture and therefore a rarer but larger magnitude event. When you allow such linking, the probability of very large earthquakes increases compared with models that treat segments in isolation. The 72% figure for a region typically represents the aggregated probability that at least one earthquake exceeding a certain magnitude threshold will occur somewhere in the region within a specified time window, often 30 years. It does not mean there is a 72% chance that a single catastrophic rupture will simultaneously flatten every city in the region on a particular date. Rather, it is the probability that some segment or combination of segments will release the accumulated strain to the degree that the regional threshold is exceeded during the interval. Because these forecasts must merge many uncertain pieces, fault geometry, the likelihood of linkage across step-overs, the distribution of slip magnitudes, the efficiency of stress transfer, and the conversion of source rupture into ground shaking at specific locations, the reported probabilities change as knowledge improves. New imaging that reveals previously unmapped shallow faults near urban centres, new paleoseismic dates that revise how often a segment fails, or better constraints on slip rates can nudge probabilities up or down. That is normal science. Models update to reflect the best available data. The practical implication is clear: a substantial probability for significant shaking on the scale of decades is a call to prepare, to harden infrastructure, retrofit vulnerable structures, and plan emergency response for a set of plausible rupture scenarios that include single-fault events, multi-fault-linked ruptures, shallow urban faults, and dynamic effects such as rupture speed and basin amplification. Returning to the San Andreas-Calaveras junction, the takeaways are concrete. The junction is a structural node where the geometry of the fault planes, the presence of lubricating serpentinite and other rocks, and the existence of cross-cutting faults beneath the surface combine to make rupture behavior complex and potentially interconnected. Parts of the Calaveras show surface creep while deeper portions may be locked. Parts of the nearby San Andreas are creeping, but adjacent patches remain locked and capable of large ruptures. The result is that the junction and its neighbouring strands contain seismic gaps, stretches that have not ruptured recently relative to geological or paleoseismic expectations. Those gaps, together with the realistic possibility that ruptures can jump across linked faults, make the junction region a place worth watching and preparing for. The precise timing, however, remains unpredictable because the crustal system is a non-linear, heterogeneous, frictional network where small perturbations can tip behavior in different directions. In short, California's seismic threat is the sum of many interacting faults and gaps. Mapping, trenching, geodetic monitoring and dynamic rupture studies have moved the science well beyond simplistic single-fault narratives. We can now identify where strain accumulates, where coupling changes with depth, and where subsurface structures raise the odds of multi-fault linkage. We can also translate those physical realities into probabilities over policy-relevant horizons to guide engineers and planners. That is the honest and actionable message. The plates continue to move, elastic strain will be released, and within the coming decades it is scientifically likely that portions of the state will experience significant earthquakes. The 72% probability often cited for a given region and magnitude threshold is a compact expression of that likelihood derived by aggregating the contribution of each known fault segment, its slip rate and paleoseismic record, and the plausible ways segments may rupture individually or together. It is not a date, it is not a promise of a single cinematic megaquake, but it is a robust alarm bell that should motivate preparedness, resilient design, and continued investment in high-resolution fault imaging and rupture physics. So communities are ready when the inevitable strain release occurs. If you're enjoying this deep dive into California's fault system, don't forget to like, share, and subscribe. And hey, tap that hype icon to boost this video so more science lovers can discover it. Your support helps this channel keep shaking up the science world.